Okay, hello and welcome back to another episode of the AutoML seminar. So today we have Julian and Ricardo. Julian is a PhD student at the University of Freiburg under supervision of Frank Carter, and Ricardo is currently a postdoc at IIT in Italy under Massimiliano Ponti. Both of them are previous Amazon interns. And yeah, today they're going to present their recent work on in context learning for Mamba, which is a new architecture that gained a lot of interest recently. And yeah, very much looking forward to this talk. And with that, please take it from here.
Yeah, thanks, Aaron, for the introduction. The talk is going to be structured in two parts. I will first talk about the reasoning behind Mamba and why it might be a good alternative to transformers. And later on, Julian will talk about our results and the in-context learning setup. And so this work was in collaboration also with Simon Schrodi, Thomas Bronx, and Frank Hutter. And they will be presented at the Mathematical and Empirical Understanding of a Foundation Model workshop at ICLEA in the upcoming month. Okay, so let's start. Both Mamba and transformers are sequence-to-sequence models. And in particular, they both work by first taking, and they have both been proposed as language models. So they take a sequence of originally of text as input, and this is passed through an encoder. Then you have a series of layers, as is standard in deep learning, and these are usually very they have the same architecture for all these layers. And then you have a decoder which outputs again a text sequence. In this case, in this example, is shown like a potential output for the as a prediction for the next token. Both of these models have been introduced in the context of models like ChatGPT that are trained to predict the next token. In particular, the transformer architecture works as follows. So each of the layers are the concatenation of an attention module and an MLP module. The attention module takes this sequence of a real dimensional vector as input, x1 to xl, and it computes an operation which works across the entire sequence to output the vectors y1 up to yl. And then the MLP module takes each element individually and applies an MLP to each element of the sequence individually. In this talk, I will refer to the elements of the sequence as tokens. So the attention mechanism has been probably one of the main contributors to the success of the transformer, and we will see in a moment why. And like more recent model, they try to be so like models like Mamba or other type of RNN-like model. They try to basically replace the attention operation with something that is more efficient. So in particular, if we take a closer look to the attention, in this case, I'm showing the causal self-attention that you use, for example, in ChatGPT. For each element of the sequence, you first compute query keys and values, which has a simple linear transformation of the token xt, where these matrices WQ, WK, and WV are learnable. And then what you do is you compute the output yt as a linear combination of the values, where basically the weights of this linear combination are computed by first taking the scalar product of the query vector kt with all the key vectors up to the current time step, and then applying a softmax operation, which is simply this exponential operation and this normalization. So this allows basically the output to be in a sense well behaved, because the weights will be between 0 and 1, and in particular they will be in the unit simplex. So this operation has some key advantages, which is that it can be heavily parallelizable, because each So each of these, so the main bottleneck is computing the attention weights alpha ti, and in particular these are L squared weights, where L is the sequence length. But each of these weights can be computed in parallel, and so this is probably why Transformer has been so popular, because this can also be used like efficiently in modern hardware such as GPU or TPUs. And the complex, but like a negative aspect is that the complexity scales quadratically with the sequence length. And this is both in terms of time and memory complexity if you want to have a parallel algorithm. Although for the memory complexity, you can have a clever implementation which actually it only scales linearly with the sequence length in the memory. The time complexity still remains quadratic. So another way of doing this sequence-to-sequence operations, instead of using the attention, could be to use recurrent neural networks. So recurrent neural networks have been like proposed for a long time. For example, LSTMs are from the late 90s. And they basically work in a different way by computing at each time step, by updating at each time step an hidden state, HT, as a function of the previous state and the current token, XT. And then the output is computed as a function of the current state, HT, and the current token, XT. So this class of models has some computational advantages compared to the attention, because it scales linearly in time complexity and requires only a constant memory complexity. So in this case, it only scales with the dimension of the hidden state. And in particular, if you want just to compute the next token, given the previous state, this can be done in constant time. So in time that is only proportional to the dimension of the hidden state. The disadvantage is that this class of methods have been notoriously hard to parallelize and to train. And this is because unless G has a special structure and you have like some clever way of initializing the weights, in particular W1, you might have problem with vanishing or exploding gradients and long computational graph, which may also cause like some numerical errors. A solution to these problems of RNNs and a way to bridge the gap between attention and recurrent models has been to have like a simpler, basically a simpler rule for the update, like a simple rule for the update of the state in RNNs. And for example, several methods have been proposed which are linear time invariant RNNs. And these are characterized by having the state update which is linear in the previous state. So as you can see, HT is simply a linear function of HT minus 1. And the matrices A, W1 and BW1 are in this case are constant with respect to the time step t. So these models are, for example, linear attention, RetNet, or S4, and some of these are a state space model, which I will dive more into data later. And more generally, you can also have the matrices A and B being time varying. In this case, the state update is always linear with respect to the previous state, but the matrices are time varying. And this allows more flexibility. And for example, Mamba fits into this kind of view. In particular, this kind of let's call them linear RNN can be easy to train if the matrix A and B are properly set and initialized. Maybe they can also be structured, for example, diagonal or triangular. In particular, the matrix A, if it's structured, this can be it can be more efficient to compute it and easier to train. And also, interestingly, they allow efficient parallel algorithm, which is called the parallel scan, which scales linearly with the sequence length, L, and it only requires log of L sequential steps. So you still get a very good degree of parallelization for this class of models, but you have a linear scaling in the sequence length. However, they are less expressive than nonlinear RNNs. There has been a paper that came out like a couple of days ago that shows this. And they also need to compute and save a potentially large state, probably also because they are less expressive than nonlinear RNNs. Moreover, transformers can also be seen as a special kind of RNNs. For example, you can view the previous keys and values of the transformers as the NNN state, which scale with the time step though. So it's not a constant, it doesn't have a constant dimension, but scales with the time step t. This work by Kataropoulos et al. Has shown that transformers are essentially equivalent to linear RNNs, but with an infinite dimensional state. So to recap, nonlinear RNNs are hard to train and difficult to parallelize, and their time complexity scales linearly with the sequence length, which is a positive thing. Transformers instead are the state-of-the-art in language modeling, and they are easy to train and to parallelize. However, they scale quadratically with the sequence length in terms of time complexity. And linear RNNs instead are both easy to train and parallelize. We will see in a moment how to make them more easy to train. Their time complexity scales linearly, so they are sort of a trade-off. Like they have they try to have both the advantages of transformers and RNNs. However, so linear RNNs, they have an advantage only when the dimension of the state is less than the dimension of the, so the advantage in time complexity is when the dimension of the state is less than the dimension of the query times the length of the sequence. However, the transformers can also be seen as linear RNNs with an infinite dimensional state. So there is a trade-off when you pass from the attention to the linear RNNs, which is that you use actually a finite dimensional state. State space models are a special class. So Mamba is a state space model, and the state space model are a special class of linear RNNs. In particular, their theory comes from the signal processing literature. The aim, and it goes as follows. So you start from a continuous time signal xt, and you want to map it to the signal yt through the higher dimensional state ht. And this is done as the linear ODE that is shown in this slide. So as you can see, this ODE is linear because the derivative of the state h is a linear function of the state of the state. And the matrix A and B are learned and usually structured and initialized so that HT is an optimal compression of the signal, of the past signal, so the signal up to time t. So this, so in particular, there is like a nice theoretical framework which is called, is dubbed HIPPO, which is a higher order polynomial projection operator, which tells you basically how to set A and B to make it, to have this property, so to initialize it as to be the optimal compression. So now I will dive a bit more into the detail on how this works. So first you choose a metric which tell you, you choose a measure that tells you how much you should prioritize previous time steps. This metric is called mu-t, and for example, here you can see like an exponentially decaying measure, which is the green one, and instead in the blue one is measure which only consider a fixed time window, and it's uniform in that time window. Then from this measure you set a scalar product and corresponding L2 norm with respect to the scalar product. So then you select a set of polynomial which determines a space of function where you want to do this projection. And these are, for example, they could be polynomials or warped polynomials, so polynomial after some transformation or some Fourier basis. And so you define this space GT. And in particular, these polynomials are orthogonal with respect to the measure. So in the image, you can see the exponentially scale Legendre polynomial or the truncated Fourier, which are respectively orthogonal with respect to the exponentially decaying measure and with respect to the fixed measure that you saw in the previous slide, to the fixed window measure. So then you define a projection as follows. So this projection operation is basically the orthogonal projection of the past signal to the space GT defined by the polynomials. And this projection is orthogonal with respect to the norm defined by the measure that you choose of the importance of the past. And then you define this operation, which is simply computing the coefficients of the function g, which is input to this operation, with respect to all the elements of the basis. So then the hypo operator simply sets ht as the composition of the two operations, and as input you take the signal x. So in particular, if you after setting all this framework in place and selecting appropriate choices for the measure and for the for the basis, you can have that HT as a closed form structure as a structured linear ODE. So it's structured in the sense that the matrix A and B and C that you saw before they have, for example, A can be diagonal or triangular. And this gives you also a nice way to reconstruct the past signal as a linear combination of the basis in GT, where the coefficients of each basis function are given by HT. So here I just show a visualization of what I explained before. In this case, the measure is the exponentially decaying measure, and the signal, the input signal is the one in black, while the reconstruction is the one in red. Instead, the state HT, I just showed the first 4 components in blue. You can see that since the measure is exponentially decaying, you have a very accurate reconstruction of the recent past, and a more coarse and exponentially worse, let's say, reconstruction of the more the farther you are into the past. So this framework is used to initialize the state space model, and then after this you start the learning. But this guarantees you that during training you have an easier time. So these models are easier to train also because of this kind of initialization. So a particular type of state space models are the so-called linear time invariant state space models, which are where A, B, and C they do not vary with the time step t. And these are, in particular, admit a convolutional form, which is the one on the right, which can be efficiently implemented using the fast Fourier transform, which is a parallel algorithm. So A, B, and C, as I said before, they are usually structured, for example, diagonal or triangular, and they are initialized using the theory, the hypo theory. But then when you want to compute, to actually compute these updates, you discretize the continuous state space models. In particular, you set a discretization parameter delta, and what you recover is essentially a linear, in this case, a linear time invariant, RNN, where the matrix A bar and B bar are simply the discretized version of the matrix A and B. And in this particular case of linear time invariant SSM, you also get the formulation as a discrete convolution, which can be implemented efficiently. In particular, the discretization here on the bottom is called the zero-order hold, and is very similar of what is used in Mamba. Okay, so but linear time invariant SSMs are nice. They can be efficiently computed, but they have like some issues. In particular, they cannot selectively ignore tokens, so element of the sequence, since B bar is actually time invariant. So this means that during the update, you cannot, for example, selectively ignore some ads or copyright information if you are processing text. Because the matrix B treats each token in the same way. Similarly, the state cannot be reset because the matrix A bar is also time invariant. So Mamba proposes to solve this problem by having a time varying A bar and B bar, essentially, and also in this case also C is time variant. So in particular, A bar depends on the discretization parameter delta t, which is time varying, and B bar depends on discretization parameter delta t, and also on the parameter bt, which is also time varying. And how are they time varying? So bt, ct, and delta t, they just depend on the current token xt. In particular, they do not depend on the state, since you still want to retain a linear state update to make it efficient. And from the theory, from the hippo theory, you can initialize A as a diagonal matrix. So this allows like a faster computation. And the hippo theory also gives you a way to initialize the parameter B. And in particular, the initialization for A is the same as the S4D initialization, which is a diagonal version of the S4 model, which is a precursor of Mamba, which is linear time invariant. Okay, so having this selectivity actually allows you to, so having this time variance allows you to have, allows you to solve the problems that I mentioned before. And this is done, so you can view it if you set, for example, n equal to 1, a equal to -1, and bt equal to 1, you get that the update of the state takes this form, where the parameter gt, if it's set to 1, you simply, you are resetting the state essentially, because this term is set to 0, while this other term is set to 1. While if it's set to 0, you are effectively ignoring the current token. And given the particular expression for delta t, gt is actually constrained to be between 0 and 1. So this is essentially a gating mechanism with this, which is similar to the mechanism, for example, in LSTMs or GRU, which are non-linear RNNs. Of course, the Mamba block, it also contains, so as the transformer block contains an MLP part, also the Mamba block contains an MLP part, but this is somewhat fused together with the SSM in this way. And you also have a convolutional, another convolutional block. And then the Mamba architecture is simply the stacking of all these Mamba blocks, very similar to the transformer architecture. So what are the advantages in practice for Mamba? So you can see that the parallel scan operation allows it to be more efficient than transformer. In particular, in this graph, they are more efficient at all sequence length. But of course, you can see that the more like the longer is the sequence, the larger the gap between Mamba and between the SSM and attention. Furthermore, if you set the sequence length to 800 and like to more than 8,000 in this case, you can see that Mamba has a very good scaling curves. So this is the perplexity of on the pile, which increases with the number of parameters of the model, and it has a better curve in this case, also better than like a fairly strong transformer baseline. And it also outperforms like all previous, so all of these other models are actually linear RNNs that were previously proposed. So Mamba has shown like a very good promise in text application, and also more recent work has also been applied to, for example, to images. Yes, so this ends my part of the talk, and now I will leave the stage for Julien.
Great. Thank you, Ricardo. I'll just move over to you. All right. I'm going to continue with in context learning. which is the property of large language models or transformer-based models that we are interested in, and that's why we did the whole project. So as a definition here, in context learning, it's the ability of a model to learn tasks from input examples in the forward pass and without updating the weights. This was first discovered or first found out to be the case in GPT-3 by Brown et al. A few years ago. And ever since then, ICL has become a major area of research. If you since it's an AutoML seminar, a couple of prominent examples are, for example, PFNs or TabPFN or Optformer, which leverage ICL in order to carry out the tasks, for example, tabular classification in TabPFN. So we wanted to understand whether Mamba is a possible replacement for transformers, for example, in TabPFN. But before we wanted to evaluate it on TabPFN, we wanted to initially understand, is it even possible to do ICL? Because it wasn't really clear based on the predecessors like S4 whether that's actually the case. And in the Mamba paper themselves, the authors themselves, they didn't really fully evaluate whether ICL is possible and only did one toy example. So what we wanted to do is to do this in on two more challenging tasks, and we chose simple function classes and simple MLP tasks. Simple function classes were proposed by Garg et al. They are basically machine learning data that is synthetically generated based on machine learning models such as linear regression or decision trees. And this setup allows us to understand a bit better whether Mamba and Transformer could perform comparably here or also match the underlying ground truth model. And we can also understand what happens in the intermediate layers as we perform the forward pass, because all the reasoning has to happen in this forward pass. And the second task that we looked at were simple NLP tasks, which were very recently compiled by Hendel et al., among others. And basically, those are very simple problems in the NLP regime where we can leverage the existing Mamba checkpoints, which were pre-trained on the pile, to compare to other transformer-based large language models, which were also pre-trained on the pile. And you can see one of the examples here. In this case, we have a country to capital mapping task, and we give us a certain number of examples of this, and then it has to carry out the task. But first of all, I'll talk about simple function classes. So in the simple function classes setup, we we generate synthetic data based on some machine learning algorithm. Let's say in this case, for simplicity, it's linear regression. So we sample linear regression data. In order to do that, we sample weights for each dimension in our feature space. So it's we always used a 20-dimensional linear regression space. So we sampled 20 different weights and generate our data based on these. Then we train a causal model, which was in the Garg et al. Case a GPT-2 model, and in our case a Mamba model. So both of them are causal, and they are not full self-attention, not unlike TabPFN, for example. And then we pass in all the different data points here in some random order and try to predict based on the X, the Y in the data set. And obviously, as we go through the sequence, each data point here knows about all the preceding points, and the predictions can become better. Finally, once we trained this model, we are in inference and we sample new test weights from the new test linear regression weights, and then we evaluate how well our causal model generalizes to these new problem instances and whether it learned some kind of general algorithm here. To draw a little bit more on the pre-training here. Sorry, actually. So this is like for those of you who are familiar with the PFN setup. This will look very similar because in the PFN setup we have they defined these priors which should be as wide as possible, so that the PFN can actually generalize to new data in the real world. And that's also the difference here to what we're doing here, because in our case we want our priors in a sense to be very small, because we want to understand very well what's the underlying model, and does the causal model capture the underlying model, and how well does it generalize. So coming to the pre-training, like I said, we sample this data, we pass it through the model. Each data point here always knows about the preceding data points, and then the predictions can become better as we grow in the sequence length. When we compute the loss, we compute an average loss across all the different predictions done in the sequence. And then we compute an expectation over many different problem instances, which we can sample very efficiently, like in the Garkadal setup. And okay, it's just the examples seen during training. So coming to our first set of results here. In this example, we trained on linear regression, and then we tested also on linear regression data here. This is linear regression with 20-dimensional feature space and no noise. And we can see here on the x-axis the number of in-context examples in log scale, and the y-axis the squared error. We can we tested we have a baseline least squares model here, which is optimal in this case, and the transformer, the Mamba, and the S4 model, which as Ricardo mentioned, is a predecessor to Mamba, which is linear time invariant. So it's a predecessor. If we can roughly split the discussion here into two parts: the left part, left of this line, and the right part of this line, because this is the number of examples that the models saw during training. If we first focus on the least squares case here, so we can see this red line here in the background, which has zero error at 20 examples. Which makes a lot of sense because it's least squares and we have a 20-dimensional feature space with no noise. So at 20 dimensions, it can fully recover the underlying linear model from which we sampled the data. And we can see that the transformer does a very good job at capturing this trend as well. It doesn't exactly get 0 here, but it follows the least squares model very faithfully. Mamba similarly, so very similarly to a transformer model. But then you can see that the predecessor to Mamba, S4, doesn't do this at all. It doesn't achieve good performance at 20 examples, and even at 40 examples, which was the number of examples that we used during training, we don't see comparable performance between Mamba and transformers. If you now look at the right side of the plot, so when we evaluate on more data points than we actually saw during training, then we can see that the S4 model fully fails here. We can see that the Mamba and transformer both length generalize to a certain degree, which is roughly twice the number of examples saw during training, so like up to 80 examples. But then the 3 seeds that we evaluated for Mamba diverge quite a bit, and for the transformer, one of them, and eventually the other 2 also. So this was just in the setting when we train on the same setting and then also evaluate on the same setting. Sticking with linear regression for one more example here. When we still train on noiseless linear regression, but then we test on noisy linear regression, where we used Gaussian noise. We still compare the same models here. So if we focus on the least squares model for the beginning, then we see that we get this double descent behavior, which is a well-known phenomenon because we're in a noisy setting, but we use a noiseless least squares model in a sense, one that isn't like a rich regression estimate, which can't adapt to this data. So it gets very bad performance here, and then eventually it smooths out the noise. So that's how this double descent behavior occurs. And we can see that the same behavior also occurs for transformer, which was also found by Garkadal back then. So we see that there's a clear double descent behavior. And for Mamba, it's the same, although it's a little less pronounced. So again, the Mamba and the transformer model both follow the least squares estimate quite faithfully. And in terms of length generalization, both degrade quite a bit here. Coming to one more example. So moving on to slightly more interesting or like slightly more complex data sets. So in this case, we sampled from ReLU neural networks. So we sample ReLU neural networks, like 2-layer ReLU neural networks with random initialization and ReLU activation function. And then we trained as a baseline a 2-layer neural network with gradient descent on this data, least squares estimate as before, and then also the transformer and the Mamba model. And we can see that the Mamba and the transformer model both follow the 2-layer MLP very faithfully. I think what's especially interesting is here that the Mamba model, which is the dotted blue line, and the transformer model, which is the orange line here, actually become better as we increase the number of in-context examples, even beyond the point where we saw when they saw during training. So it seems to be something that actually can leverage new data as well here, which is probably the case because of the more complex data. All right. So the other question that we wanted to understand in this setup is, how does the transformer do this all in the transformer or the Mamba model do this all in one forward pass? Because it has to identify the model and then optimize something and then actually come up with a solution here. So we wanted to understand, how does Mamba approach the solution during the forward pass, or similarly also the transformer. And we used a method that is inspired by something that was proposed by w.r.t al in 2021. So essentially, we have this our architecture here, which where we have a certain number of layers of Mamba layers or attention layers. We have an embedding layer that maps to the embedding space, and we have an unembedding layer that maps from the embedding space to the output space. And in this case, in our case here, the unembedding is to the output space is just a scalar, because we just map to a scalar here. So the idea is that we use this unembedding layer that was already learned for the output also on the intermediate layers, assuming that there's some kind of shared structure there. So we use this decoder there and decode the intermediate representations. We can do that very easily, and then we obtain some GZLI here for each layer. But before we can actually, we can't directly use it. At least that's what we hypothesize here. We need to adjust it for some scale and shift, because we can't really expect this to be in the same order of magnitude as the output directly. So we have these two parameters, AL and BL, which we need to estimate for each layer in order to get our intermediate prediction. So in coming to our results here, so we used the same setting as before. We are in a linear regression setting. We used 40 examples. We use 10 additional examples to estimate our scale and shift parameter, which are just scalars for each layer. And then we use 50 data points on which we evaluate how well or what the intermediate prediction, what the error of the intermediate prediction is. So coming to our result, we have on the x-axis here the ratio of layers, which is essentially the point to which the forward pass has come. So if you look, so the Mamba layer here, so we use 24 layers for Mamba and 12 layers for the transformer in order to keep the number of parameters similarly. That's why we have double number of dots here for Mamba as crosses for the transformer. And we can we called it the ratio of layers, so that we can plot them in the same graph and compare them as the distance between the input and the output. And on the y-axis we have the squared error. So what we see, and for the transformer especially, is that the transformer relatively smoothly approaches the solution that it finds at the end here. You can see this very nicely in the green curve. And for the Mamba layer, you can see that it does something similar at the beginning. Then towards the end, there's a sudden jump, and then it gets a relatively comparable solution to the Mamba to the transformer model. So we can see that in both cases, the Mamba and the transformer seem to iteratively approach the solution during the forward pass. Coming to our second example here, where we're still using linear regression data. And it's still two models which are trained for 40 in-context examples. But we want to see what happens for length generalization, because we saw in our previous plots that length generalization for linear regression data doesn't work so well, because sometimes the curves diverge. So the data here actually for the Mamba on the left and the transformer here on the right, and the blue curve here is the same one that I showed you in the previous plot on the previous slide. And then we use the same model, but we evaluated it at 80 in-context examples and 160 in-context examples in the same setting that we also had on the previous slide. So we can see that for the transformer, the performance degrades as we increase the number of in-context examples, like pointing to this length generalization issues. So we get worse performance even though we show more data. And for Mamba, we can see something very interesting, namely that the performance degrades quite a bit already for 80 in-context examples. And then for 160 in-context examples, we see a kind of divergence within the layers. So as we move through the network, it seems to approach the solution initially, but then fail to do so and then diverge completely within the network. length generalization fails due to divergence in the forward pass. All right. So this was about simple function classes. I'll briefly now talk about the simple NLP tasks, which were compiled by Handel et al. So these NLP tasks are structured into 4 different categories. We have algorithmic, where it's about a list element extraction. So you get a list of characters and a number indicating the index of the element that you want to extract, and the output needs to be the element in question. You have translation from English to Spanish, for example, linguistic, such as like having a word from singular to plural, and knowledge-based, like the country to capital mapping that I had in the examples before. So what we benchmarked here is the Mamba models at various sizes, which were pre-trained by the Mamba authors on the pile, and one additional one was also fine-tuned from the pile, then on the Slim Pajama dataset. And all models are shown 5 in context examples here. So starting with the first set of results. So when we have here on the x-axis the accuracy, and we show these box plots with the median shown here, we can see that as we increase the Mamba model size, or as we use larger models, the performance increases as like very smoothly as we increase the model size, exactly what we expect. But it's nice to know that this holds in this case, and the models seem to work very well. And we can see that the Slim Pajama model seems to work slightly better even than the one that was just trained on the pile. When we compare to RWKV, which is another scalable transformer alternative, which a lot of people were talking about on Twitter, here in the V4 version, we can see that the performance of these models, which were also pre-trained on the pile, is not really comparable to Mamba at equivalent model sizes. We can see this especially here, for example, for 4.3 billion open for like 430 million parameters, you can see that the difference between this one and 370 million for Mamba is already quite big. If we now compare this to Llama, then we can see that Mamba seems to work reasonably comparable to Mamba to Llama, even at high number of even at like much larger model sizes. But as you can see, there's a point of diminishing returns here, and these simple NLP tasks are probably not hard enough to really bring out the difference between Mamba and Llama here. Finally, we also evaluated whether what happens for these checkpoints when we increase the number of in-context examples and compared Mamba and RWKV here. So we have here a 370 million Mamba model and a 430 million RWKV model, which is the blue line and the yellow line. And we can see that the Mamba model consistently outperforms this model. So RWKV was significantly worse, and even a larger RWKV model only slightly outperforms the Mamba model at much smaller sizes. All right, coming to our conclusion here. So Mamba was proposed as a much more efficient transformer alternative for long sequences, and we found this to be the case. We evaluated on simple function classes and simple NLP tasks to test whether Mamba and transformer perform comparably on ICL tasks, and we also found Mamba to not have any consistent disadvantage there. And we also found that from this interpretability angle, that similarly to transformers, Mamba also approaches the solution iteratively internally. And finally, since this is an AutoML seminar, again, the setting that we were interested in here for the AutoML perspective was to understand whether this would be a way to unlock larger data sets in TabPFN, where we could potentially scale to like maybe 100,000 data points. Thank you very much.